Okay. Well, this is very exciting, this conference. When it was first cooked up about 2 years ago, I think it was Jean-Michel and Jeff who were talking about it. We got very excited about it. It's been a lot of work, and I think it's been a lot of fun at the same time. We're looking forward to a really good meeting. I'm going to thank the people who've been helping me here on the site over and over again, because they've been so wonderful. In particular, Lucille Nisi and Amy Della Russo and Ramon Di Castillo have been just an immense help. I'd be lost without them. I'm probably lost anyway. At any rate, Jeff and I have decided to consecrate this first hour and a half to a discussion of the mathematical work of Jim Simons. This is work which is very close to both of our mathematical lives and played a tremendous role in both of our mathematical lives. So in fact, I mean, this was one of the easiest talks for me to prepare in some time. So I'm going to begin by discussing Jim's work in the field of minimal submanifolds. So let me begin by describing, maybe we should have less light. Begin by describing the classical Plateau problem. So the classical Plateau problem in Euclidean space is something we all easily understand. I mean, you give yourself a boundary, compact submanifold of some dimension p, embedded in Euclidean space. So there it is. And you ask for a spanning surface of dimension p plus 1, which has area less than or equal to all other possible spanning surfaces. Now, classically, you'd like these. Classically, you'd like these spanning surfaces to be as nice as possible, and but even in the simplest case, where the boundary is just a curve in R3, sort of proving that such a thing exists and is regular turns out to be quite a difficult task. And in fact, Jesse Douglas got the Fields Medal for doing this in the first case. Now, when you think about this, there are several questions. I know people hate it when you do it, but I'm going to do it anyway. The first problem is just the question of existence. Given this boundary, do you have something which spans it? And it turns out that, in fact, there was a general theory due to Federer and Fleming that asserted the existence, in some weak sense, of a solution to the Plateau problem. So these solutions, while they always existed, were rather like weak solutions to partial differential equations. You've got them, there's this nice space in which they live, they're almost what they ought to be, but they ain't quite what they ought to be. And so you're left with proving regularity for the solutions. I mean, you have a weak object which solves this problem, then it should be better than its competitors. And well, regularity, it turns out, is a difficult question in this case, because we already knew that if you're in codimension 2, you can't expect this thing to be completely regular. It's not going to be a submanifold. If you just look at the complex cone in Cn, which is given by the singular quadric, this already has the property that any piece of it is a solution to the Plateau problem for its boundary. It's sort of globally volume minimizing, and it's singular. It's not a manifold, at least at one point. And this is archetypical of many examples. I mean, in fact, every complex analytic subvariety of Cn is a solution to the Plateau problem locally and, in fact, globally. On the other hand, it was conjectured that in codimension 1, life was a lot better. But in codimension 1, you might actually expect the solutions to the Plateau problem, when you were taking really area minimizing things, to be nice embedded submanifolds. Well, they may have integer multiplicities for coincidence reasons. I won't worry about that, but they should really be nice. And in fact, this was proved. It was proved in the unoriented case by Reifenberg, and in the oriented case by Wendell Fleming for n equals 3, and it was extended by Almgren to 4 space for three-dimensional objects in 4 space. And that's pretty much where it stood for a while. So now, let me talk a little bit about, I'm going to talk a little bit about the generalities of minimal submanifolds. So first of all, what are the properties of any solution to the Plateau problem? Well, one obvious thing is that if you take a one-parameter family of deformations, a one-parameter family of diffeomorphisms of space, which fixes the boundary, and you look at the volume of this deformed object, well, since at time t equals 0, you've got a minimum, the first derivative of the volume will be 0, and the second derivative is going to be non-negative. Now, when you're actually looking at a manifold solution, then you can integrate by parts, and when you integrate by parts, it turns out that this first equation, 1, can simply be written as shown, where V is the variational vector field. It's just that you look at where the point goes under the deformation, and H is an intrinsic vector field, the mean curvature vector field that's defined in terms of the geometry of the submanifold as it sits, the metric geometry of the way that manifold sits in Euclidean space. Now, if you have this equation for all deformations, you easily, for all vector fields along the manifold which vanish at the boundary, then you easily see that this mean curvature vector field is 0. And the vanishing of this vector field constitutes essentially a quasi-linear elliptic system of partial differential equations. I mean, the system has reparameterization invariance, but you can get rid of that by, say, graphing this manifold over its tangent plane at some point, and then it actually becomes explicitly a quasi-linear elliptic system. And there has been in place for a long time an elaborate theory that applies. So, and in fact, you know, for example, that C1 alpha solutions are automatically real analytic. The problem is to actually get them to be something so nice as C1 alpha. Now, all of this can be generalized. I mean, we could have not considered Euclidean space, but we could have considered instead some ambient Romanian manifold, and they're given a boundary and tried to solve. And this enhanced problem has two nice features. In the new problem, you get to actually specify the homology class. So if you give your boundary here, you can actually ask that the solution be homologous to that curve. So anything, all the competitors you're going to look at have to be homologous to this one. That is, they have to satisfy the fact that the competitor minus this bounds. And another nice thing is that you can actually forget the boundary and just try to minimize in a homology class. Now, I think that, so one can actually, for example, think of these things, solving the Plateau problem in a homology class as the higher dimensional analog of looking for closed geodesics. And I think this was something that occurred, one of the things that occurred to Jim Simons at a certain point early on was that if one looked at these things, one should be able to do a lot of geometry. I think one of the things that's typical of all of his contributions to mathematics is the vision. And Jim had a certain vision of what this meant for Romanian geometry and where it could go. And he set about trying to do something about it. He sat down and just began studying the problem of minimal submanifolds in Romanian spaces, something that nobody had really done. And it just transformed the field. So let me describe the one thing that we're going to have to discuss a lot, and that's the second fundamental form. So suppose you're looking at a submanifold M. So let's just make the picture. You've got M sitting in M bar. And did I just lose something? Yeah. All right. So if you take a pair of tangent vector fields to M and take the covariant derivative, one with respect to the other, using the ambient covariant derivative, you don't get something which is tangent again. The tangential component is the Levi-Civita connection of the induced Romanian metric, as we know. The normal part gives you something which is actually a tensor. It's a zero-order operator, even though it looks like a first-order operator. So just this normal component, the excess component of covariant differentiation along the submanifold, gives you something which is a symmetric two-form on the tangent spaces with values in the normal space. So now if you take the trace of this, you get a normal vector, and that normal vector is the mean curvature vector. It's that simple. But the whole second fundamental form is this symmetric bilinear form on the tangent space with values in the normal space. So it generalizes the classical shape operator that you see in any book on surfaces in 3-space. And this B satisfies 3 equations, which I'm not going to bother you with. One is the Gauss curvature equation, in which it relates, there's a relation between the curvatures of M, M bar, and B. And there's also a normal curvature equation. And then there are the Minardi-Codazzi equations, which are certain first-order equations, which I like to think of as the sort of compatibility conditions. They're like the Bianchi identities in Romanian geometry, or simply the fact that d squared is 0. So these are things which are just there because of the way the thing is defined. Now, what Jim realized was that if you take the minimal surface equation and you combine it with the Minardi-Codazzi equations, you essentially have a Laplace equation. Now, I mean, you think of the, here, this is not at the moment defined, but you can think of the Minardi-Codazzi equations as the analog of dB equals 0, and the minimal surface equation is the analog of del B equals 0. And of course, if you do that, then you can write down the usual Laplace operator, which is d del plus del D. And the sort of amazing insight he had was that these 2 equations really meant that this satisfied a harmonic condition. And then he said, I don't know what he said to himself, but this is the way I always imagined it, that, although it didn't read this way in the paper, that you can apply Bachner's method, right? So what's Bachner's method? Bachner's method is you look at this Laplace operator and you re-express it as the crude Laplacian plus a curvature term. So you've got this standard harmonic Laplacian, and if you subtract off the crude Laplacian, you get some expression in curvature. And now you've got 2 positive operators, 2 non-negative operators here, and a curvature term, and you're going to get global implications of curvature. So he sat down, rolled up his sleeves, and came up with the equation. And this is the nicest form of the equation you're ever going to see. I mean, actually, to define this, the right-hand side of this equation, this curvature term, takes pages and pages and pages in this Annals paper. It's not so bad. It's got cubic terms in B, and it's essentially linear in curvature. But when the ambient manifold is constant curvature, constant sectional curvature, and you're looking at a hypersurface, this thing really drastically simplifies. It becomes this very beautiful equation. Norm squared B minus n times the curvature times B. And on the other hand, it's not linear. And the nonlinearity is what really makes it interesting. So let's just take this case, and let's in fact look at the sphere where the curvature is 1. And if you let me put this back up here. So if you take that equation, right, multiply by B, take the inner product with B and integrate, you get this, okay, obviously. So let me put this up here. And now, let's just stare at that for a minute. So this is simply taking the inner product with B and integrating. Now, the second equation up there simply defines the crude Laplacian. The crude Laplacian is exactly defined by that equation. You apply the formal adjoint of covariant differentiation. It's a very strongly positive operator. Now, obviously it's greater than or equal to 0, but the left-hand side is not obviously greater than or equal to 0. And in fact, you see that you get immediately the following consequence, which was quite a surprise. Namely, if you have any closed minimal submanifold of codimension 1 in the sphere, the norm of whose second fundamental form is everywhere less than or equal to the square root of n, then it's actually totally geodesic. So it's a great sphere. And Jim actually proved this in more than codimension 1. A similar theorem holds in all codimensions. So it's a kind of isolation theorem. It says that you can't get close to the great spheres with any closed minimal submanifold. Anything which is, so morally speaking, anything which is very close to them has to be it. Okay? It's a quite surprising thing. Now, not only did he prove this theorem, but it turns out that this is sharp. I mean, you can ask, is this the best bound? And it certainly is. If you allow b squared to be exactly equal to n, then there is a whole flood of examples, and they're all given by these generalized Clifford tori. So we're in the unit sphere in Rn plus 2, say in the, is that what I want? Well, yeah, right. And so I want to look at an n-dimensional manifold in Sn plus 1, and I simply take the Euclidean coordinates and split them in half and take a sphere in here and a sphere in there, and I can adjust the radii, and there's exactly one adjustment of radii that makes it minimal. And for those, the norm squared of the second fundamental form is identically equal to n. So it turns out that these examples are really very important. They're not just... Okay. So now, one of the reasons that minimal submanifolds of spheres were important is because they come up, because of the following construction. I mean, you can take, given any submanifold of the sphere, you can take the cone on it. You've got the submanifold of the sphere, and you just look at the union of all the rays through that submanifold. That gives you a cone in the ambient Euclidean space. And it's not difficult to see that this submanifold of the sphere is a minimal submanifold of the sphere if and only if the cone is a minimal submanifold of Euclidean space. Now, cones are particularly important because they arise as the sort of first-order approximations to solutions to the Plateau problem. And if you have a solution to the Plateau problem, these cones that you get are not just, they don't just satisfy first variation 0, they satisfy the stability condition that the second derivative of area is greater than or equal to 0. So one of the main results of this paper that Jim wrote on minimal submanifolds said that if you have a submanifold of codimension 1 in the n sphere, which has the property that the cone on it is not just minimal but stable, so the second variation is greater than or equal to 0, so it looks like a local minimum, and if n is less than or equal to 6, then this thing is totally geodesic. It's a great sphere, and therefore the cone is a plane. It's a hyperplane. It's a hyperplane. And he also went on to observe that if you look at these Clifford tori, for example, S3 cross S3 and S7, this is the first dimension where the theorem doesn't apply, then these cones are stable. So there's this very definite dimension cutoff, which was really a big surprise. I mean, people did not expect this to be true. Now, this result had two big consequences. The first was that this result I talked about of Reifenberg and Fleming and Almgren, which held in dimension 3 and 4, now can be extended to dimension 7. That is for n-dimensional manifolds. For n-dimensional manifolds in Rn plus 1, where Rn plus 1 can go up to 7. So the answer now is that if you solve the Plateau problem in Euclidean space, in codimension 1, and you're in a Euclidean space of any dimension less than or equal to 7, you have complete regularity. You get a nice embedded submanifold everywhere, analytic. And now let me indicate sort of how this goes. I mean, what you do is to blow up. I mean, you've got this solution. You take a point on it, and you look at the family of dilations at that point. Now, dilations in Euclidean space preserve all these properties. I mean, if you have something which is minimizing and you dilate it, it's still minimizing. It's got a bigger boundary. So if you take a sequence of these dilations, the theory allows you to conclude that there are subsequences which actually converge. And what they converge to are, again, things which are minimizing, but they're cones. They're cones. So you get these limits which are actually minimizing objects, but they're cones. Now, they're cones over things which are just as bad in the sphere. But when you have a cone, you've actually gained 1 degree of regularity, because the cone direction is nice. it's sort of a factor, a Euclidean factor. You've reduced it down. And once you can reduce the problem down, you can go by induction. I mean, we sort of know what's true in dimension. We have the result in dimension 2, and you can go up. But at every stage, what you need to know is the following. When you take this limit and you get a cone, you need to know that the cone is smooth outside the origin. So if you have, by induction, the regularity theory in lower dimensions tells you you've got something which is smooth outside the origin, and now you can apply Jim's theorem, and it says that it's actually a plane, because it's stable. But if it's a plane, then the technology of regularity theory tells you that it's actually a submanifold. This is the key thing that you need to know. This goes all the way back to Reifenberg. So it was always important to know that the tangent cones were planes. And that's what it gave you. So in these dimensions, we actually had this. Now there's another classical and beautiful theorem in the theory of minimal surfaces, the Bernstein conjecture. And so the Bernstein theorem, which was proved in 1915 by the Russian mathematician, I think it's Sergei Bernstein, anyway, says the following. Suppose you have a classical function of two variables, x and y, defined in the entire plane with the property that its graph is a minimal surface. So that means it's a global solution to the minimal surface equation. Then, in fact, that function is linear. That's Bernstein's theorem. Or another way of saying it, the graph is a plane. And this is a theorem that enjoyed a lot of generalizations, and most of the arguments were done by a complex analysis. But Wendell Fleming gave a proof which was pure, which was really free of complex analysis, and it was that proof that was able to be generalized. So it was first De Giorgi who realized that this could be used to prove the Bernstein theorem, that is a function in R3 whose graph is a minimal surface has to be linear. And Almgren extended it to n equals 4, and Jim Simon's results allowed you to extend it to dimensions 5, 6, and 7. And let me give you an idea of how that goes. In this case, instead of blowing up, you blow down. So you've got this graph of a function defined over all of Rn, and you pick a point as an origin, and you begin to shrink. You begin to shrink. Well, when you shrink this thing, it's still a minimal submanifold. And again, you can take limits. And when you can extract sequences of limits. And the limits, again, will be cones. The limits, again, will be cones. Now, if you have this regularity theory, the regularity theory tells you that the cone is actually smooth. And not only that, it's stable. Oh, by the way, there's a fact that goes back, I think, to Fleming. Whenever you have a minimal surface, which is a graph of a function, it's a one variable in terms of all the others, so it's a hypersurface. Whenever you have a minimal surface, which is a graph, that's always minimizing. You just translate the graph up and down. It gives you a foliation, and the tangent planes to that give you something called a calibration. And there's an old trick that allows you to show that it's minimizing. So these graphs are always minimizing. They're always solutions to the Plateau problem. And so when you bring them down, you get a cone which is minimizing. Since it's minimizing, you have interior regularity. You can show that it's regular, and now you can apply Jim's theorem, which says that if it's a cone and it's regular outside the origin, well, you can just say if it's a cone, it's not regular. But in fact, you can go a little bit further. You get one additional dimension, because if you have regularity only in one dimension lower, you can claim that this cone is at least smooth outside the origin. And then also, because it was a limit of a graph, its normal vector makes a positive inner product with respect to the z-axis, and that allows you to conclude that it's a product. You reduce the thing down by 1. So the Bernstein theorem holds in dimensions up to 1 dimension greater than interior regularity. Now, I think one of the most surprising things about this story was that not only did Jim's work extend these results through some range of dimensions. I mean, a lot of times mathematicians go ho-hum, all right, now we've got it up to 17, and what do we do next week? But Jim actually proved it to the point where it was, to the limits in which it was true. And it was his example of the cone on S3 cross S3 that I discussed that actually showed that this was the best possible. That cone on S3 cross S3 is a solution to the Plateau problem for its boundary. This was celebrated work of Bombieri, De Giorgi, and Giusti. And they at the same time showed, by sort of using that cone and solving the minimal surface equation, they also showed that the Bernstein theorem fails in all dimensions above 8. So it was kind of a spectacular result because it showed us that this phenomenon does not persist. There's something about space that changes in this minimal surface game, much more reflective of what happens with differentiable structures. As you have more and more room, things change. Okay, so the second thing I want to talk about is the question of stable currents. So let me.
Is there a connection between the two? Did they happen in the same dimension, possibly?
Yeah, well, Jim used to have some really neat ideas about this, but no one has ever really made it work. Yeah. It's sort of, I think one of the things you mentioned once was to sort of graph a diffeomorphism, an exotic diffeomorphism, and try to show it can't bound a disk, and that has something to do with regularity. But, anyway, it's still a really intriguing question. All right, so let's go back. So as I said, one of Jim's ideas was that one should actually use minimal subvarieties to probe the structure of Romanian spaces, the way you use closed geodesics. And so we have these conditions, first variation 0, second variation greater than or equal to 0. And this makes sense not just for submanifolds, but it makes sense for anything that you can measure, right? I mean, you move around and take the derivatives of its area. And a nice class of such things are the things called rectifiable currents. So if you know what they are, that's fine. If not, you should just think of them as sort of manifolds with corners and worse. Technically, it's a certain closure of the Lipschitz chains. So you allow things which are as bad as push forwards of simplices or of manifolds with corners under Lipschitz maps. And there's a lot of structure for these things. This is what hardcore geometric measure theory is all about. But just let's think of these things as manifolds with singularities, but which have a notion of boundary. And you can look at these things with orientations, and you can take coefficients in groups. They're very, very general. Now, if we think of the sphere, then I like to see what happens to these things in general. And one can consider the space. There's a certain natural family of flows on a sphere, the flows that come from height functions. So for every linear function in Rn plus 1, when you're sitting on the n sphere, you can look at the gradient of that, and that generates a flow which has a source at the south pole and a sink at the north pole, and we're all quite familiar with how it goes. And now, given any one of these flows, and given a current, you can take the volume of the current, deform it by this flow, take the second derivative, set it equal to 0, you get a number. Now that number turns out to be a quadratic form on this finite dimensional vector space of vector fields. I mean, this vector space is just Rn plus 1. That's the ambient space of linear functions. And the amazing thing is that the trace of this quadratic form is a negative multiple of the mass. It's a completely universal statement. So it doesn't matter how bad your object is. You can take your manifold and break it into little pieces, and this still is true. And one of the things that this says is that there are no stable rectifiable currents on the sphere. And now, for any finitely generated abelian group, so this proves the homology of the sphere is 0 if you had doubts about it. But one of the things is that you can take the same technique and apply it not to submanifolds of spheres, and not to the sphere itself, but you can take submanifolds of spheres. Okay? So suppose you have any submanifold of the sphere, and then what I'm going to do is to take currents in there, and I'm going to deform them according to the same vector fields. Well, these vector fields don't preserve the submanifold, so you do the obvious thing. You just take the tangential projection of such a vector field. It now generates a flow that preserves the submanifold, and you play the same game. Now, what comes up is that the geometry of the submanifold in the sphere is going to play a role. So there's a certain quantity which is defined above. I mean, if you take a point on this, you take a point on M, and you take a tangent p-plane there. Take an orthonormal basis of that tangent p-plane, and look at the unit p vector that you get by taking the wedge product, and then take an orthonormal basis of the orthogonal complement. And using the second fundamental form, you make up this quantity. Okay? And it turns out that you get this very, very nice formula that if you take the trace of this quadratic form that you get by taking the second derivative of mass, it's again an integral over the manifold, or more generally over this rectifiable current, of this thing applied to the tangent space minus PQ. And so again, if this quantity B is small, you've got a theorem. And so, for example, the obvious thing to do is to just take the maximum of this thing, and then, by the way, if you take the maximum of this thing on these unit p vectors, you get a norm, and the norm is related to the usual L2 norm by this formula. Now, from a formula of this kind, you clearly get that if this norm is strictly less than PQ, then there are no currents in dimension P or dimension Q, where P plus Q is the dimension of the manifold, which are stable. And now, because we have these solutions to the Plateau problem in any homology class, that says these homology classes are empty for any finitely generated abelian group. And that has some nice implications. I mean, it gives you some not completely obvious results about submanifolds of spheres. So, for example, an easy thing is that if the norm squared of the second fundamental form satisfies this inequality, then you're looking at a homotopy sphere. And this is an inequality which allows negative sectional curvatures in general. So it's not a... and let's see, other things that it also yields results like this. If you have a submanifold of the sphere n plus k, then, and you look at the you look at the minimum squared principal curvature over all normal directions. So you assume that this is a very curved submanifold. Then if that minimum norm squared of the principal curvature satisfies an inequality of this sort, you can prove by this method that the top Stiefel-Whitney class is 0. Now, for anything which is an embedded manifold, the top Stiefel-Whitney class is 0. So you get a result. And in fact, you get a result for also for surfaces, because it's an easy calculation. So, so in fact, this.
What's the last corollary?
Oh, last corollary is that if you look at a surface immersed now, it doesn't have to be embedded, immersed in S4, then there has to be some principal curvature which is less than or equal to 1. It can't be. And I think, in fact, the Veronese embedding is sharp. All these things are sharp. So the Veronese surface has principal curvatures everywhere 1. It's homogeneous. So then any other surface that has to... So now, on the other hand, Jim also had realized the importance of minimal surface theory to complex geometry, and he had a real vision for what this could mean too. And so in the same spirit, one can look at complex projective space. Now, in complex projective space, we have these natural vector fields, namely the Killing vector fields. Those are the infinitesimal isometries. They generate one-parameter flows which are metric preserving. But in complex projective space, if you multiply such a vector field by I, then you get a very different kind of flow. You get something which is actually a gradient. So let's look at those flows, those gradient flows that come from the infinitesimal isometries. It's a finite dimensional space, and we can play exactly the same game. Take any rectifiable current, take the second derivative of its mass, and you get a quadratic form. And lo and behold, that quadratic form satisfies this equation. It's, again, less than or equal to 0, but the term now can actually be 0. It has to be, because the complex submanifolds of projective space are all area minimizing. But it turns out that this quantity that we're taking the norm squared of is just the following. When it sees a p vector, it simply acts on it as a derivation. Now, that gives you some element in wedge p. You take its norm squared. The nice thing about this is that it's 0 if and only if the plane that you're looking at, which is a real p-plane, is in fact a complex p-plane. So p has to be even, and it has to be invariant under the complex structure. So this guy is strictly negative on every current except those which have the property, the very special property, that every tangent p-plane is a complex plane. Now, that turns out to have very strong implications. There's a deep theorem of Harvey and Schiffman, which says that if you have a closed rectifiable current that satisfies this condition, then it's an algebraic cycle. And it's an algebraic cycle in the sense that it's an integer linear combination of algebraic subvarieties and not necessarily positive integers. So this is a complete measure theoretic characterization, just in terms of deformations with respect to holomorphic vector fields, of algebraic cycles in projective space. And it's one of the few that I know that really doesn't use positivity. I mean, it's just a second variation characterization. It's a very nice result, I think, and I think Jim had a lot of hope for it vis-a-vis the Hodge conjecture. I mean, if you have a submanifold of projective space, then you can characterize the algebraic cycles in there in essentially the same way. Their volume has to be stable with respect to holomorphic deformations of this variety in the bigger space. And it would be really lovely to see this carry through to give a nice characterization of algebraic cycles in projective manifolds, but so far it hasn't worked. It's because Jim left mathematics. So the last thing I wanted to mention, and then I'm going to sit down, is something which is not, which you're all quite familiar with. Back in 1975, Jim and Frank Yang ran a lunchtime seminar over a period of weeks, in which I understand the idea was that the mathematicians were to explain to the physicists what they were doing, and the mathematicians were never allowed to ask questions. And conversely, the physicists were to explain to the mathematicians, and physicists were not allowed to ask questions. And at the end of this, I gather, they had made this absolutely amazing discovery that a floor or so away, they were doing exactly the same thing. The connections, which is what Jim was working on at the time, were exactly the same thing as gauge fields in physics. And as we all know, this had fundamental consequences worldwide. I mean, Yang and Wu went out and wrote this dictionary between connections and gauge fields, and Jim talked to Singer and Atiyah, and they got very interested in these problems, and they got lots of other people interested, and there has been this enormous renaissance of coming together of mathematicians and physicists, and it's certainly been great for mathematics. Anyway, Jim also at the time did some work on this, which you may or may not be aware of, but he again went back to the sphere and said, well, look, let's look at Yang-Mills fields over the sphere. So in the Romanian case, Yang-Mills field is simply something which associates to any principal bundle, any connection on a principal bundle over a Romanian manifold, the L2 norm of the curvature. And now one's interested in critical points of this functional. And again, a critical point is like a minimal submanifold. It's a critical point. And you'd like to know you're at a local minimum. That means the second derivative is greater than or equal to 0. So let's call those stable. And Jim proved this very lovely theorem that on the n-sphere, when n is bigger than or equal to 5, there are no stable Yang-Mills fields. They're all unstable. N equals 4, we know it's false. And in fact, Jim's methods inspired Bourguignon, and I had a little to do with it too, to actually show that in that case, the stable ones are self-dual or anti-self-dual, the only ones that are positive. But so again, Jim's work was really inspirational and set off a lot of interesting things. Okay, that's all I have to say. I'm going to turn the field over to Jeff, who's going to, or should we take a break? What do you think? I think we should maybe just go on. Yeah. So sorry.